We were talking last time about the nested intervals property of the real numbers. Actually, our book refers to this as the NIP, the N-I-P. I don't know if I like the sound of that, but this is what the book says, the nested intervals property. And I hope you remember what it says. It says, like, the picture to have in mind is it's about if you have a whole bunch of nested closed intervals like this, and you take the intersection of all of them, they go on, there's infinitely many of them, and you take the intersection of all of them, you want to know what points are in all of them, and the theorem says, the nested intervals property says that an intersection, if I have like this, I'll write it as intersection IN, where n goes from 1 to infinity, of nested closed intervals. Nested means each one is contained inside the previous one, and therefore inside all the previous ones. And closed, of course, means the intervals, include both of their endpoints. Anyone remember what's the conclusion about the intersection? It is not the empty set, right? That's what the theorem says. This is the nested intervals property of the real numbers. And the I said one specific example last time was if you take the intersection, if you use the intervals 1 over n to 3, each time here the interval goes all the way up to 3, but it starts at 1 over n. I think I said minus 1 over n. Did I? Doesn't really matter. Anyway, if you do this intersection, it's true you will not get the empty set as the answer. In this example, actually, you get 0 to 3, right? You're just asking which points are in all of those intervals. All those intervals include all the positive numbers between 0 and 3. They also all include the number 0, but they don't all include any specific negative number, all right? I don't know if that's obvious, but I want you to think about it a little bit. I thought maybe as a little warm-up today to get us going, I would like you all to try to think of some more examples sort of this type. I want to try and think about what kinds of things could the intersection look like. In this case, the intersection is a closed interval, but I would like to try and think about what else could the intersection look like. So here's a little question I would like you to think about. So can you make an example? By make an example, I mean you think of some kind of sequence of nested intervals. Can you make an example where, how about the intersection is a single point? Can you make an example where the intersection is a single point? Or how about, these will be separate examples. Can you make an example where the intersection is the empty set? This one we can answer immediately. The answer is no. That's what the theorem says. The theorem says you cannot make an example where the intersection is the empty set. So I'm just going to immediately say no, because that's the whole point of the NIP. The nested intervals property says that you cannot get the empty set when you do an intersection like this. How about, I have another, what about, can you make it so that the intersection is an interval, but not a closed interval? You'll notice in that example that I did last time, you get an interval, and it happens to be a closed interval. I wonder, is it possible to make it an interval, but not closed? And then I got one more. How about one last question? What about if the intervals themselves in the intersection are not closed intervals? So how about using non-closed intervals, can the intersection be empty? Right, the nested interval property says if they're all closed intervals, then the intersection cannot be empty. But what if maybe the intervals themselves are not closed to begin with? Then can the intersection be empty? This is what I would like to know. So see what you think. I'll give you a few minutes to think about these. You can talk to your friends about it. I'm going to walk around and you can talk to me about it too if you want to. See if you can come up with some other examples. Just play around with the intervals that use the intersection. See what can happen. Maybe some of these are impossible, right? Like certainly that second one that I wrote no on is impossible. Maybe some of the other ones are impossible too. We'll talk about it in a moment. Yes.
Infinity sign on top. Does it always have to be an infinity sign on top? That kind of like it.
In this theorem, it is always infinity. But so the big intersection sign works kind of like a big sigma, like a summation. Sometimes you can add up to infinity, but you can also stop.
Okay.
So, yeah. But the nested interval property is always going up to infinity. That's just 0, 1.
I was going to say exactly that.
And the intersection.
Yeah, I don't think that's possible.
Any thoughts? Yeah, I like that. That's good. Any thoughts? For this one, to get a single point, straight down. They still all go up.
But like that's something that is this is what I'm saying.
Yeah.
And that's the only way we have one to do it. I don't think it has
How's it going? This one is possible. It is, yeah. You have
I don't know, I'm just thinking like as long as it's the same process.
know what I got. I just want to. So this might, but I don't know if that is not.
Yes.
Yeah. So the problem, the interval needs to be different. Here's my suggestion. The example that I put in negative 1 over n, as the n increases, that way shrinks the thing down. But it's still over the 3 over, so you only have shrinking one side of it. If you want to get a single point, try and make it so that, both sides are same.
So one's getting smaller. I was gonna say, I was thinking it had to be always. Yes, I'm finally done. Not that I need to think about it. I think more. So they really.
Yeah, that's it. And then what is the intersection then?
No, that's where I'm from. Yes, and then of course.
All right, let's talk about these. I know a lot of people figured out the first one. I don't know about anything else, but I saw several people came up for the first one. You want the intersection to be a single point. My hint to various people was, like the example that I gave, the circled one, these intervals are shrinking but only on one side, and so eventually all those intervals are always going to include like all the numbers from 0 to 3. But if you shrink the interval on both sides, you might be able to make it so that it gets down to just a single point. And I think the simplest way to do that, so for the first one here, maybe I'll do like this. The intersection is a single point. I'll just write my answer right next to it. Whoa. So for this one, how about intersection of, this is the most natural way to do it, I think. So the first interval is -1 to 1, and then the next one will be -1/2 to 1/2. These are getting smaller every time. And what is the intersection then? There's only one number that's in all of these intervals. 0, yeah. So the intersection, writing it as a set, should be technically written this way. It is the set with a single element, and that element is 0, okay? So it is possible to get a single point as the intersection. Excellent. So is it possible for the intersection to be empty? That is not possible. It's not really obvious, but that's the nested interval property. You cannot make the intersection empty. How about, can you make the intersection into an interval that's not a closed interval? Did anybody have any thoughts about that?
I said negative n and n.
Negative n to n. I think this is a good idea, but that is not those are not nested, because the n minus n to n.
Yes.
Yeah, these actually get bigger every time when the n increases. You need them to get smaller every time. Yeah, that's not a bad idea, but well, it's a bad idea, but I appreciate the idea. No, it's not a bad idea. It's just wrong. Any other ideas? Yeah.
About like n to infinity. Do that.
N to infinity. Okay, this is also an interesting idea. It's an interesting idea. That's what I should have said. You want like this?
Yeah.
Yeah. So those are not closed intervals. If you close off the one on the other side, like this, these don't really count as closed intervals. Although it's still interesting to think about. These are nested. They all go out all the way out to infinity, and they start at n. So every time these get smaller, what is the intersection in that case? Anyone else can say too. What if I take the intersection n to infinity? On a number line, what these look like is, so the first one, say, starts at 1 and just goes on forever. The next one starts at 2 and goes on forever. The next one starts at 3 and goes on forever. What would the intersection be? That is, what are all the numbers which are in all of these? Is there any number you can think of that's in all of these intervals? I think there is not any number that's in all of these intervals. So actually this, the intersection here is empty. This would seem to contradict the nested intervals property, but these don't count as closed intervals because they go out to infinity, and that doesn't count as a closed interval as far as the nested intervals property goes. So this is not not really addressing this this question about can you make the intersection into an interval which is not closed. Actually, I'm here to tell you, it is impossible. You can't do that. This, for reasons which are not, this is not something that really we can explain in just a moment right now, but I'm just going to say this is impossible. It is a fact, and it's kind of a big theorem, that any intersection of infinitely many closed intervals becomes a closed set. And what a closed set means is it's either a closed interval or a single point, which are the options that we've already discussed. So this is not possible to make an interval that's not a closed interval. All right. How about the last bit there? Can we make the intersection empty if perhaps we use intervals themselves which are not closed? Anybody think about that? Actually, this example that he said before will work for that. If you allow the interval to go out to infinity, then you can actually get the set to be empty. Did anybody come up with another example for this? You can actually do this without using infinities. Non-closed intervals. Can we do this without infinities? Actually, I think the example I was thinking of had infinities also. Anybody have another thought? No. All right. I don't either. I'm satisfied with this. So, great job. Any other thoughts about these? I thought it might be nice to just play around with some of these nested intervals. All right, the nested interval property is kind of a big deal. We're going to use it. It's not the kind of thing that we're going to talk about all semester long, but at least I know it's going to come up next time. It's a great little fact. It's one of those things that doesn't really. It seems just sort of weird and doesn't seem like it would be so important, but it turns out to be pretty deep, I would say. All right, let's talk about something else then. We ready to move on from the nested intervals? All right. Let's talk about the sort of major topic for today is what we call the Archimedean property. These are all like basic properties of the real numbers. We had the completeness axiom, and the completeness axiom we used to demonstrate the nested intervals property, and also we're going to use the completeness axiom to demonstrate the Archimedean property. And the Archimedean property is about, I'm going to say in vague terms, this is about how the set of natural numbers, that is, 1, 2, 3, etc. It's about how the natural number sits inside of the set of real numbers. All right. The Archimedean property is meant to express a fact that everybody knows. This is about how the natural number sits inside the real number. So, because you've been coached from a very young age, you think of the real numbers as being a line, which this is a correct view of the real numbers. You think of the real numbers as being a line, and you think of the natural numbers as sitting inside that line, sort of evenly spaced like this, right? These are the whole numbers. And I suppose, let's say 0 is here. The natural numbers only includes the positive, 1, 2, 3, 4, etc. All right? The Archimedean property is a description that tries to describe sort of the way that this picture looks, in the sense that we expect the natural numbers to be sort of evenly distributed throughout the positive real numbers. No matter how far down the line you go, there's still going to be some natural numbers sitting there, and they're always like spaced out like this. All right, this is what the Archimedean property is about. And also, at the same time, the Archimedean property describes where the fractions live, the fractions of the form 1 over n, where n is a natural number. So the fractions, they all live like right here, right? These ones are, this is the set 1 over n, where n is a natural number. All right? So there's going to be two forms of the Archimedean property. There's kind of the big version, which tells you about where the natural numbers go inside the real numbers. And then there's the small version, which tells you about fractions of the form 1 over n. And they all kind of are stacked up by the 0 there, all right? This is the idea behind what the Archimedean property is going to say. It's trying to express those two ideas. Like I said, These are things just because of your upbringing, they seem obvious to us all, because this is how you've been taught, even as a kid, to think about numbers as on a line. But, these are things that people had to sort of discover or state formally. So I'm going to give a formal statement here of the Archimedean property. I don't know, actually, I should have looked up the history on this. I don't know if, to what extent Archimedes is actually responsible for these ideas, but for some reason it is named after Archimedes. So it has two, this is statement number one. There's going to be two of them, and I'll call this the big version. The big version says that for any real number, x, basically, I'm saying here, no matter how far down the real line you go, if you go out to the right, no matter how big your number is, there's always going to be some natural number that's bigger than any given real number. For any x in R, there exists n in the natural numbers such that n is greater than x. All right? No matter how far down the real number line, there are still some natural numbers bigger than any given real number. You have to imagine you're like a person who has never heard of the real numbers before, and I'm trying to explain to you how the real numbers work. It might occur to you to ask, like, is there such a thing as a real number that's just bigger than every natural number? And the answer is no, there isn't. You might say, what about infinity? And I would say, forget what they told you on the playground, but infinity is not a real number, right? It's a concept. It's a real thing, but it doesn't count as a real number. Okay, this is what I call the big version of the Archimedean property. And then here's the small version, and this has to do with fractions. The big version basically says there are natural numbers bigger than any real number, and the small version says there are fractions that are smaller than any real number. So this one says for any x in R, there exists n in the natural numbers such that n is less, sorry, not n, 1 over n is less than x. And I have to say, sorry, I forgot, for any x in R with x greater than 0. All right, I'm talking about positive real numbers. There is a fraction which is less. So this one, you want to imagine that x is something really close to 0. No matter how close it is to 0, there's still going to be some fraction, 1 over n, which is smaller than x. All right, this is the small version of the Archimedean property. These are both statements about kind of where the natural numbers live. There are really big ones, and if you take the reciprocals, they're super small, right? Yeah?
For the big version, can't you say like the same thing but like swap? Like for all natural, there's a bigger real?
Yes, the big version, yeah, for every natural number, it's true there is a larger real number. That is actually very easy to show because the natural numbers themselves are already real numbers. So you can just say any number n has some number n plus 1, which is bigger, right? But if I give you a real number, x, it's not so clear. How do you tell me what's the next biggest natural number than x? That's because you can say, well, yeah, x plus 1 also exists, but that's not a natural number. That's another real number. So it's that's a little trickier. Yeah. Great question. Let's see if we can do it. So the Archimedean property, the first one, these are not really very difficult to explain why, although it has to do with the completeness property though. These things are not true without completeness. So I want to talk about, let's talk about the proof for number 1, and then actually number 2 you get kind of for free from number 1 by just taking a reciprocal of everything. But we'll see when we get there. Would you mind if I rephrase the big Archimedean property in this way? It says for any real number, there is some natural number that's bigger. Another way of saying that is the set of natural numbers is not bounded, right? Because if the set of natural numbers was bounded, it means there's some real number that's bigger than all of them. But what the Archimedean property says is there is no real number that's bigger than every natural number, right? So for the first one, I'm going to say I want to show that n is not bounded, right? Not bounded above. That's what this statement says. It says no matter how big your natural number is, no matter how big your real number is, that real number cannot be an upper bound for all the naturals. There's always some natural that's bigger. All right. So we want to show that the natural numbers is not bounded above. We do this by a contradiction. So I'm going to say, for the sake of obtaining a contradiction, assume that n is bounded above. And immediately we are going to use the completeness axiom. Does anyone remember what the completeness axiom said? The AOC? Yeah.
It says something like if it's not empty, then the suit of A exists. And there's no.
Right. So if A is a non-empty set which is bounded above, then the sup of A exists. That's what the completeness axiom says. Now, we just said assume that n is bounded above. So I'm going to say, by the axiom of completeness, what does it mean? Since n is bounded above, it means the sup of n exists and is a real number. So by the axiom of completeness, I'm going to call it, let's say, S equals the sup of n exists. Now, this is not true. I only wrote that because it follows because of my contradictory assumption here. I'm going to derive a contradiction. The sup of n means the least upper bound for the set of natural numbers. The sup of n exists. All right. How does this lead to a contradiction? Like, you should already feel like this is not possible. The sup of n means the least upper bound for the set of all numbers. This would be somehow some real number which is bigger than every one of the natural numbers, which there is no such thing. But how can we say that? So I'm going to say then S minus 1. S is supposed to be the least upper bound for the set of natural numbers. That means S minus 1, I guess, is not an upper bound for the set of natural numbers. So S minus 1 is not an upper bound for n. So that means there exists some number n such that S minus 1 is less than n, right? If S is the least upper bound, then S minus 1 must not be any upper bound because it is less than S. And if it's not an upper bound, that means there is a natural number bigger than S minus 1. Then you can just sort of add 1 on both sides. S is less than n plus 1. And this n plus 1 is in the natural numbers. So S is not an upper bound, and that's the contradiction. So at some level, the proof does boil down to like something like, this is like, kids on the playground talk about this. Sometimes people ask me, is there any such thing as the biggest number? And I say, no, because you could just add 1 to it and you get a bigger number. So there is no such thing as the biggest number. I suppose there's such a thing as the biggest number that anyone has ever written down or something like that. That would be a foolishly big number, but there is no biggest number, all right? This contradiction shows that the set of natural numbers is not bounded above, all right? Any thoughts about that? Questions? Put this in the category of things that everybody knows is true, everyone who's ever thought about it at least, but requires some justification. Okay, I said part 2 you get for free if you already had part 1. Can we just talk a little bit about part 2? So for part 2, I will say informally at least, you just do reciprocals of everything. So remember, what I want to show is that for all x in the real numbers, there exists x being positive, there exists n in the natural numbers with 1 over n less than x, all right? The trick is to take the reciprocal of everything and then use part 1. So we're going to say let x be in R, then consider 1 over x. Like for this part, you think of x as being a really small number. When you consider 1 over x, you're suddenly looking at a really big number. Then by part 1, can anyone tell me what does part 1 tell us in this situation? Part 1 is about big real numbers. And 1 over x will be a big real number. So what does part 1 tell us? Yeah.
So it's gonna be a natural number bigger than a real number?
Yeah, part 1 says no matter what the real number is, there's a natural number that's bigger. So in this specific case, if I'm considering 1 over x, I can say there exists n such that 1 over x is less than n. That's what part 1 says. Any real number has a natural number that's bigger. All right. Any thoughts? How can we get to the end here? Look at what I said we needed to show there. What we want to show is here, 1 over n less than x. Can you get there from here? Yeah.
Take the reciprocal of that inequality.
Yeah, this inequality here, you just take the reciprocal. Am I allowed to do that?
You have to switch the sign.
Take the reciprocal on both sides of an inequality. Can you do that? You got to switch the thing or not? A little deep thoughts for a 7th grader or something. This is one of those things that I feel like ought to be obvious, but it isn't so obvious. Can I say, just because that makes me a little uncomfortable, how about we multiply both sides by x first? Let's just do individual things here. Can we take this inequality here, multiply both sides by x? It says 1 on the left side and then nx on the right side. Somebody tell me, do I need to change the direction or not? No, why not? Yeah, because we assumed in the theorem that x was positive, right? This is important, but I do not need to change the direction. Okay, and then what? Now divide by n. Do I need to change direction then? No, why not? Yeah, n is a natural number, which means it's positive. So do that. So 1 over n less than x. This is what we wanted to show, right? Tune. All right. The inequalities are a little mysterious sometimes. All right, this is the Archimedean property, the big form and the small form. Now when people ask you, is there such a thing as the biggest number? You know what to say. No, there isn't. All right. We got 15 minutes left. I don't know if this is enough time to talk about in full detail about what I wanted to get to, but I want to talk, we got 14 minutes left, about something like the Archimedean property, but about rational numbers inside of the real numbers. So you know, if someone were to ask you to describe how are the natural numbers living inside of the real numbers, you would say something like they're evenly spaced and sort of evenly distributed among the real numbers, you know, like 1 apart every time. What about the rational numbers? How would you say the rational numbers live inside the real numbers? Remember, the rational numbers are all fractions, right? I would say something like the rational numbers are sort of everywhere inside the real numbers. Not that every real number is a rational number, but they're just like, they're packed in there somehow. This is what this next theorem is about. I'll write the theorem, although we're not really going to do a proof. There's a word for this sort of packed in there. It is the word that we use in analysis is dense. So Q is the set of rationals, Q for quotient. Q is dense in R. And what that means, this is a description of sort of how the rationals are distributed inside the set of real numbers. I.e., what this word dense means, at least the way that I'm using it here, is for any A and B real numbers with A less than B, there exists a fraction m over n in Q with a less than m over n less than b. So the sort of slogan form of this is between any two reals, there is a rational. Actually, between any two reals, there are infinitely many rationals, but what we're saying in this theorem is just between any two real numbers, there's always a rational number in between. All right? I remember when I was going to grad school, like when I was getting ready to go to grad school, I met some grad students, and this one guy impressed me with his math joke about the downtown area. I don't even remember what city this was. He said, "Oh yeah, we got a lot of Thai restaurants downtown." He said, among the restaurants, the Thai restaurants are dense. And then just because he wanted to impress everybody, he had to explain himself. What I mean by that is between any two restaurants, there's a Thai restaurant. That's what dense means. We were all impressed by this guy. I hope you are similarly impressed by this guy's undying humor. Dense means between any two real numbers, there is a rational in between. And the same is true the other way around. Between any two rationals, there's a real number in between. We got 10 minutes. Maybe we could talk, let's just try and sort of look at a very concrete example of this fact, and then we'll get back to showing why exactly this is true. Maybe we'll do that next time. But how about a very specific example? For example, I actually used my calculator on this one. Can you believe it? We're not often going to use our calculator in this class. Let's consider two real numbers, one being pi and the other being 22 over 7. Maybe you know that 22 over 7 is pretty close to pi. This, for a while, was sort of a rule of thumb approximation to pi, 22 over 7. These real numbers are close together. They are not equal. So I'm going to say they are both with an E. Both in R, but they're not equal. Does anyone know which is bigger? Any fans of 22 over 7 out there? I actually didn't. I had to plug this into my calculator. I will tell you the digits. Pi is, of course, 3.14159. I'll just do that much. And then 22 over 7, if you compute the digits, is 3.14285, blah, blah, blah. All right? Anyone want to tell me, can you give me a very specific rational number in between those two numbers? 22 over 7 already is rational, but that's fine. Pi is not rational, but anyway. Is there a rational in between? You can just tell me in terms of the decimals. What do you think? Yeah.
3.1416.
3.1416. Yeah, I think I agree. That's a little bit bigger than pi, but not so big as 22 over 7, right? It is in between those two numbers. So this is what the density theorem says. It says no matter what the two real numbers, this is always possible to do. And it might seem, I mean, if you believe that real numbers can always be expressed by decimals, then it seems reasonable that you could always do some kind of simple trick. Like how did you figure that out? It's not because he's like intimately familiar with these numbers. It's just you look at the decimals and you sort of just choose something in between. The density theorem says it is possible to always choose something in between. All right. I would like to think about how can we do this. So could we do it without knowing the decimal expansions? Sort of without looking at your calculator. Or without guessing somehow, right? Because if you want to prove the density theorem in general, you have to have some way of describing a system by which you can always find the number in between. And we're not going to rely on decimal expansions here. If I think of this like on a number line, we're talking about numbers which are already very close together. Let's say this is 3, right? And this is 4 over here. Then pi would be something like here maybe. And then this other number, 22 over 7, would be maybe there, right? They're very close together. Probably on this picture, they're actually much closer even than I drew it right there. Can you eyeball some point in the middle? Actually, we're going to use the Archimedean property to do this. The Archimedean property tells you where the natural numbers are and also tells you where the fractions of natural numbers are. But the strategy here is scale up the picture. What I mean by that is multiply everything by some really big number. Multiply by a giant number. I want to scale up the picture until the two numbers, the two reals, are more than distance 1 apart. Like the distance between them, whatever it is they have some distance between them. And I want to multiply them by some huge number to make it so that that distance goes further than 1 apart. And by that time, you're guaranteed there is a natural number in between them. And then you like scale the picture down again, and that natural number turns into a fraction, which is what you're looking for, a fraction that's in between those two numbers. Here's the idea. So we'll talk about this in more technicality next time, but we can do just in this particular example. The idea in this case is let's multiply everything by 1,000. All right, then my picture, instead of 3 here, it starts at 3,000 and it goes up to 4,000, right? Pi becomes 1,000 times pi, which in decimal digits is 3141.59, right? And then that number, 22 over 7, I'll move it over just because I can't fit it there. 22 over 7 now times 1,000, which its decimal digits are now 314, I don't remember, 2.85. These are the digits that I wrote before, all right? And now, these are far enough apart that there's going to be a natural number in between them, all right? Like right here, this natural number is 3142, right? And in fact, when we do the real proof, we'll see this is using the Archimedean property. The Archimedean property guarantees that there is a natural number bigger than this one over here. And if that distance is more than 1, it'll also be less than this distance over here. That's the trick. Anyway, now 3,142 is between those two numbers. So I can say, 1,000 pi is less than 3142 is less than 22 over 7 times 1,000. And then what's the rational that's between actually pi and 22 over 7? We can divide through the whole equation by 1,000, the whole inequality. I don't mind doing that. Pi less than 3142 over 1,000 less than 22 over 7. And this is what we've been looking for all along, right? A rational number which is in between those two numbers. Now, this is the reason I wanted to go through all this detail is because this is exactly the way that we can do it in more generality in the proof. So maybe I'll just say, I was hoping to do the abstract proof today, but can I just say this? The proof is just like that. You just use variables for everything instead of pi and 22 over 7 are specific amounts. So can I just say the proof of the density theorem is just like this? I don't think we have enough time to do the real proof in 3 minutes. But what I just said is the whole main idea. The numerator, let me just say in a little bit of detail. The numerator, I mean this numerator here, 3142, comes from the Archimedean property, the big version, right? It comes from multiplying up the scale of the entire picture And then the Archimedean property says there must be a natural number bigger than, in this case, 1,000 pi. But whatever the real number is on the left side, you use the Archimedean property to get a natural number that's bigger. And then because the distance across here is more than 1, the natural number will also be less than the other one. And then you do this little division thing, all right? The numerator comes from the Archimedean property. All right. I think I'm going to leave it at that for the theorem then. We got 2 more minutes. That's all right. I think we're done.